Today we will talk about global cooling from plant transpiration. First, we will address why it is important. Then we go into the details of this phenomenon. Then we discuss what climate models have to say and whether they have the capacity to assess it. And we conclude with implications. Recently, I noticed a very disturbing tendency in the mainstream scientific media to de-emphasize preservation of natural boreal and to a lesser degree temperate forests. I give you just a couple of fresh examples. In May 2022 in Science, there was an article with the original subtitle saying, literally, that expanding boreal forests could be a bad news for climate. Interestingly, the title was changed to a milder one. Then there is the new report, Not Just Carbon, from the World Resources Institute. It emphasizes that the positive climatic role of boreal forests is only local. You see, local is their emphasis. And from this, one can infer that since the remaining primary boreal forests are usually distant and difficult to reach, their local impact is needed to nobody, and globally, the Earth would be cooler in their absence. And indeed, the most recent study in Nature, Ecology and Evolution suggests that boreal forests are not critically needed. On the left map, the green color shows ecosystems that, according to the authors, are critically important. And whatever is the criterion of being critically important, primary boreal forests are apparently not. I know that many people in our audience are from tropical and subtropical regions. Sometimes it is like you feel automatically a relief when it is not your ecosystem that you are fighting for that is being, devalued. But this is a common problem for all people convinced that preserving functional ecosystem has the highest priority in the climate situation, what I will be talking about. Next slide, please. So we can see here that exactly what is called the critical natural assets does not include the remaining primary boreal forests. They are excluded because they are distant, and apparently their loss causes, as Wikipedia says, least concern. Okay, next slide, please. But my professional expertise tells me that de-emphasizing preservation of any natural ecosystems, be they boreal, temperate, or tropical, will seriously aggravate global especially the water cycle disruptions from which our continents are increasingly suffering. And these policies and their background argumentation need to be re-examined, and this is what motivated this webinar. So let's examine the evidence. If you had a chance to read questions submitted during the registration, many of them are about where does the heat go? Indeed, when more sunlight is reflected back to space, the planet receives less energy. So it's intuitively clear that it must cool. But while we all know that evaporation cools locally, we also know that this energy doesn't disappear, but is released somewhere in the Earth's system. Like here you can see in the famous Sternberg diagram of the radiative energy budget of the Earth, condensation releases heat captured during evaporation in the mid-troposphere. So can evaporation indeed produce net cooling? To answer this question, we will employ a simple toy model of radiative transfer. Such simple models do not give us a correct numerical answer. but they can elucidate qualitatively what happens. And please do not be discouraged by anything here. Numbers, the very few formulae or unknown terms. Knowledge empowers, and especially environmental knowledge will greatly empower our conservation efforts. So first, let us imagine a planet that absorbs the same amount of sunlight as the Earth, 239 watts per square meter, but it doesn't have an atmosphere. Then all this solar radiation is converted to thermal radiation at the planetary surface and is radiated to space as thermal photons. In this diagram, 1 stands for incoming solar radiation. So it is 239 watts per square meters, just for convenience. Everything will be calculated using this basis. And from the well-known physical law, we can calculate the surface temperature from this radiation. And it turns out 255 Kelvin or 33 degrees Celsius lower than the global mean surface temperature of our Earth. So this is like what the Earth receives from the sun. Let us now go to another planet, the right graph. When there is an atmosphere and a certain amount of greenhouse substances, this amount is sufficient to absorb all thermal radiation from the Earth's surface. Just for the record, this means that its thickness should be of the order of 1 free-path length of thermal photons. As before, the same amount of solar energy is absorbed by the surface, and the same amount of thermal energy is emitted to space. But now we can see that the thermal radiation at the surface doubles. It was 1 in the absence of absorbers, but now it is 2. And the surface temperature also has grown. And in this idealized example, it is now 30 degrees Celsius, a very hot planet. And this is what the greenhouse effect is about. By redirecting part of thermal radiation back to the Earth, greenhouse effect, greenhouse absorbers creates a higher temperature. We had a comment from John who mentioned that 2 doesn't mean twice as much, but just more than 1. This is not true. Please let us invest some effort to understand this diagram. We are on a different planet, John, compared to the left graph. And so if you look at the energy budget for each layer, it is precisely conforms to energy conservation. Take a look. This is the Earth's surface. It receives 1 from solar radiation and 1 redirected, and emits precisely 2. Take this layer of greenhouse gases. It emits, so the planet as a whole, it receives 2 and emits 2. And the planet as a whole receives 1 and emits 1. So at each layer, we have the energy conservation satisfied. It is a different planet, different greenhouse effect, and different surface temperature. And this simple but fundamental representation of radiative transfer provides us a clue. So now we come to the point. What happens when we have evapotranspiration? This is our main slide. Now we have another planet, a third one. And on this planet, we have a forest. And let us imagine, this is what we said, that this forest changes, takes 40%, 0.4 of solar energy, takes it to evapotranspiration. And then we assume that condensation occurs and latent heat is released within our upper absorbing layer. Okay, you see, so here the trend is diagram here. So latent heat is here. And what happened next? This heat, the greenhouse layer has received this heat and it radiates it up and down, like from the symmetry in equal amounts. But now we are concerned about radiation to space. And since we receive 1, we must emit 0.8 to add to the 0.2 to observe the energy conservation law. And this means that this layer emits 1 and that it emits 1 down. And now we can see that due to the presence of evapotranspiration, the radiative flux, thermal radiation from the Earth's surface has diminished compared to the upper graph. And it is now 1.6 and not 2. And we notice that it has diminished precisely by the amount of latent heat. But you can see that at any layer as before, there is a conservation net, of course. And so what happens to the heat is absorbed by the greenhouse absorbers, is re-emitted, but the surface radiation is reduced. So where does the heat go? Our response, it is ultimately radiated to space. But in the presence of evapotranspiration, the mean altitude where conversion to thermal energy takes place increases. So here, all energy was converted to thermal radiation at the surface. And so all thermal radiation interacted with the greenhouse absorbers. But here we can see that a certain part has escaped being redirected back to the Earth. And this diminishes the greenhouse effect and the planetary surface temperature. And in this sense, evapotranspiration and convection in general can be seen as a leak in the planetary greenhouse through which the energy escapes more directly to space. And we can calculate that with 80 watts per square meter as the mean global latent heat flux, reducing evapotranspiration by half on 15% of land area, historical deforestation, could oppose a forcing of about 2 watts per square meter, which is comparable to CO2 doubling. And this is approximately the figures that have been circulating, and I personally saw a similar estimate in an email from Dr. Walter Hiene. So this says that this is correct, that this is upper limit on this global cooling. So, but now we will look into some more important detail of what happens when this energy is released by condensation. And a very important point to appreciate is that the magnitude of global transpirational cooling depends on atmospheric circulation, because it takes time after the heat has been released by condensation. It takes time for the energy to be radiated to space. And you can view it like this. Greenhouse gas molecules are lazy and need to be pushed by their neighbors multiple times before they get excited and radiate. Therefore, the more time the warm air spends in the upper atmosphere above the main greenhouse absorbers, the stronger the global transpirational cooling. And long-distance moisture transport, including the biotic pump run by forests, enhances global transpirational cooling. If, on the contrary, the air rises and descends quickly, like in strong storms or tornadoes or some like violent wind events, then all the heat is brought back to the surface with the descending air, as if almost nothing happened. And therefore, this violent local rain could warm the earth by returning condensational heat back to the surface and thus negating or diminishing transpirational cooling. So this is what I have to tell you. And if you go into the detail, you might find it useful as a way how to understand this phenomena. Now we have to check what the global climate models have to say, because there is much effort put into developing these models, and they describe the atmosphere as much as our knowledge at this time permits. And so whether there is this cooling in global climate models. And also, if you look through the questions, many people have a colleague or an IPCC scientist who would be telling them that global transpirational cooling doesn't exist. But it does exist, as it is the latest, for example, latest IPCC report says, and you can see this graph to the left. It shows that according to the models, you see these small blue circles. It is by how much, this one. For example, tropical forests, by how much the Earth would warm if the tropical forests are removed. And you can see that it is like a small fraction of 1 degree. Let us now look how are these studies done. In a global climate model, the corresponding ecosystem, you can see the map, is replaced with a desert or grassland. Carbon concentration is kept unchanged. Then the model is integrated from the initial conditions for about 200 years, and the global mean surface temperature is then assessed. Let us take a closer look at one particular model. When the boreal forests are removed, see the right table, the model says that due to the higher albedo, that is, more sunlight is reflected, mostly in spring due to sufficient sunlight over the white snow cover, the absorbed solar radiation is reduced by almost 14 watts per square meter. So you can see this one. This produces a global cooling of almost 1 degree Celsius, not shown in this table, but you can check the source. For tropical deforestation, described in the left table, it is found that the absorbed solar radiation has reduced even more, by almost 20 watts per square meter. Can you see this? 14 here and 20 here upon tropical deforestation. So all this dark green stuff removed because albedo also grows. But this does not produce any cooling, although I bet that if it did, it would be readily reported that yes, albedo dominates, but it doesn't. Instead, there is warming, global warming, sizable regional warming, and although the global warming is marginal, just 0.3 degrees Celsius, it does exist, despite the radical diminishment of incoming radiation. So if you have a colleague or friend who will argue that cooling from transpiration or warming when this cooling is lost does not exist, you can refer him or her to this IPCC report that says the opposite. And it is a very strange situation which requires some, analysis, that this effect is so fully understood that even if it is formally acknowledged from model outcomes, many people just, it is so alien to their vision of the atmosphere that they will deny it. And I'm sure that in our audience, there are people who experience this. So it exists in models, but it is small. What is the reason? We can, of course, mention the insufficient model performance in reproducing key processes that affect global transpirational cooling. And as we remember, one of such processes is the long-distance moisture transport. Here you can see the bias in how different global climate models, which names are listed to the right of the graph, reproduce the continental river stream flow. The Amazonian runoff is underestimated by up to 50%, and this corresponds to an error of about 10% of all continental runoff, which is of the same order as global continental evaporation. And we have seen that just a small increment in evapotranspiration can provide a sizable radiative forcing. And here we have an error of where it is transpired and where it is transferred of about 10%. This is another illustration how global climate models consistently underestimate the destabilization of temperature regime on the diurnal scale that results from deforestation. So when deforestation occurs, we know that the maximum temperatures go up and minimum temperatures go down. So there is a destabilization, rise of fluctuations, and they don't reproduce this effect. You can see not even the sign of the effect. And this is done consistently. So imagine that we didn't have observation to check it. We would conclude from these models that there's a robust response from the models showing that this effect is small. So, but there is actually the main reason why it is small, why the global transpirational cooling is small in models. And it is not very straightforward. But I must tell you here, at least as much as they can try. So we see the skill of global climate models, their physics that they can reproduce is different for different atmospheric problems. And these two problems, increase of CO2 amount and removal forcing by land use, are totally different with respect to what models can actually model. And the problem is that calculating radiative forcing does not require an accurate prediction of the vertical temperature profile. And Arrhenius was first calculated it assuming a constant temperature profile, so that the temperature profile, you can see it on the left. This is how Earth's temperature, atmospheric temperature declines with altitude. You can see that it declines, and there is approximately the point 255 from which there is the radiation. So it is possible to get a plausible estimate of the radiative forcing from CO2, assuming that this vertical profile remains the same. And you get a first order estimate, very good. And the models are good at doing that. But look at this lower graph to the left. Here you can see that the altitude of the upper radiating layer didn't increase because we don't change the forcing that does not consist in changing the amount of absorbers. But the temperature gradient changes because now as the temperature has reduced at the surface, so the temperature difference between the upper radiative layer and the surface has diminished as well. So this effect, the first order effect, is the change of the vertical profile of atmospheric temperature. But this is exactly what the models cannot assess. And because they use the so-called convective parameterization, which determines how radiative and non-radiative sources are partitions in the atmospheric column. And for doing so, they prescribe a certain vertical temperature profile. So basically, zero order, they say, let it be constant. But if this effect of forcing through latent heat is just proportional to this change of vertical temperature profile, when the models implicitly assume that it is constant or just changing in a very little, so they zero this effect by construction. So they're made to report that this effect is zero. This is a very unusual situation, and because of that, all model outputs have very different uncertainty depending on the task that they are solving. And with regard to CO2 emissions and radiative forcing, it is okay, but everything that concerns water vapor, vegetation, doesn't have doesn't have any skill. So, and here we are done actually, and we came to conclusion. So global climate models have a major goal, and they have been built for this goal, to assess radiative forcing from increasing CO2 concentrations. And they do have this capacity. This forcing can be roughly estimated assuming an unchanged atmospheric temperature profile. And there is an independent theoretical assessment of how big this warming for CO2 doubling can be. And when the first models were built, they were referring to that Arrhenius estimate, like, something solid under your feet. Global cooling from plant transpiration is a different atmospheric problem. Transpiration control by plants can change the planetary greenhouse effect via minor modifications of the atmospheric temperature profile. Global climate models with a convective adjustment, which a priori assumes a certain critical temperature profile, do not in principle have the capacity to estimate this effect. And by construction, they report it as zero in the first order. And the conclusion about global cooling from boreal deforestation is based on this neglect of global cooling from plant transpiration. It is not reliable. Global warming from tropical deforestation is therefore severely underestimated. And now I'm reaching to our tropical colleagues. Your ecosystems are much more valuable for fighting climate change than the 50% addition to carbon storage that is generously allocated by the recent World Resources report of the World Resources Institute. Output of current models pertaining to this effect should not inform policies of vegetation cover management. Otherwise, such policies would magnify the ongoing environmental degradation and climate instability. Finally, natural ecosystems have evolved to maintain environmental homeostasis. They play a crucial role in the long-distance moisture transport, biotic pump. Given the critical state of climate and ecosystems and our limited understanding of both, the best strategy for vegetation cover management is to adopt a global moratorium on the cultivation of any natural forests, enhance their protection, and then multiply efforts on ecosystem regeneration whenever possible. We need to preserve natural forests to stop the aggravating water cycle disruptions in our teleconnected world. You can see that we are all connected by powerful streams, atmospheric streams that that make us all dependent on each other. And you can see that boreal forests are on the way, it is the way of these streams that connect our continents in the Northern Hemisphere. They are crucially important. So this webinar was meant to ring an alarm bell. We have delegated too much trust to the numbers that the models provide us with. But I do not want to sound negative, as what Ugo Bardi calls the medieval flagellants who went around shouting, "Remember that you must die." Global climate models are very powerful tools to illustrate and look into the processes that shape our climate. Their capacity should be further developed. But at this moment, we also need to continuously reassess their skills for any particular task that we are handling. Science behind CO2 radiative forcing is well developed. Science behind how the atmosphere responds to the loss of evapotranspiration, as I have argued here, is not. In this situation, we cannot sacrifice any square meter of natural ecosystem. We still have what to preserve, and we should do that. And let us change our attitude and policies starting from today. Thank you. Yeah, I'm done. Thank you very much.
Thank you very much, Anastassia. It was a pleasure to hear you. Do you all hear me? Okay, see a lot of clapping. We can clap in various ways. So let me summarize very briefly. It's what Anastassia has been telling us is that the climate system is a complex system. Doesn't have to be very complex. It just needs to be complex. And the characteristic of complex systems is that they always surprise you. We also say complex systems always bite back, which is typical of cats, which they have complex system. And the climate system is also able to bite back. And we should not assume that we know everything about these systems. In particular, evidently, we risk to underestimate how the system may react to forcings, to the various forcings that we are applying to the system, CO2 concentration, but also deforestation and other, also the disruption of the ocean systems, as we may want to add to Anastassia's talk. There is also a similar problem with the sea. The sea is also being strongly perturbed by humans, and that's a big problem. So we have to be careful, because to understand the message, we know a lot about the atmosphere and how it reacts to our perturbation, the human perturbation, but we don't know everything, and we risk to make mistakes. So it's an extremely important message, this one, that comes from Anastassia, Dr. Makarieva, if you prefer. And we have some time to discuss. Evidently, I'm sure you felt the same way I feel. There is something important here. There's something we need to understand. There is something we need to discuss. And we have some time to discuss. And we don't really have a schedule, a fixed schedule for this meeting. So I would just invite you, the panelists, but also the general public, to raise your hand and make a comment or ask a question. Or we may go directly to the questions which have already been asked, but we have many. So would somebody, before entering to the questions, make a comment of the panelists, please? Raise your hand. And
you can see Patrick has raised his hand.
Okay, Rob, I see that your hand is raised. Would you like to comment, please?
I think Mr. Patrick Worms was first.
I'm very sorry. Patrick, please. I don't know if you can unmute him. Thank you, Zuzka.
I've muted myself. Thanks, Udo. I thought that with my pink shirt, I would be the most visible of all, but here we are. Anastasia, thanks for an absolutely remarkable presentation. I'm from C4 ICRAF, and yes, most of our forests that we worry about are tropical and subtropical, but I'm also Vice President of EURAF, the European Forestry Federation, so temperate and, dare I say it, European boreal forests are close to our hearts. The question I have to you is whether this issue that you've identified with most of the climate models existing today, and notably the way that they fail to account for the temperature gradients across altitudes as the phenomena that you've identified are taken hold, are being recognized by the modeling community, and whether efforts are afoot to modify the models to begin to take these issues into account? Or are we in a situation where this is still very much a kind of science that is not widely recognized and that needs more help in being communicated to the wider scientific and modeling community? Thank you.
I would go for an answer right away. Anastasia, please.
Thank you very much, Patrick, if I may. You see, this is a peculiar situation, and the response to your question is that, yes, we do need more awareness in this issue. Because I can tell you that the climate community, taken broadly, they even deny the existence of global cooling from transpiration, not just because it doesn't exist like small, but because they think that it violates the laws of nature, like heat must be retained in the system. And
but it's based on very basic physics. It's based on very basic physics. How come that's not taken into account at all?
How come? Yes.
Taking physics into account in their modeling.
And this would be your homework. You do know one or two climatologists. Go and ask them, what can they say about this? This is one thing. Another thing is that the fact that these are two different problems. One is first order and the other is second order with respect to changes in vertical temperature profile. It is not recognized by anybody at the moment in its application to vegetation cover, policies or whatever. Generally, as I understand the situation, I'm not a modeler. Generally, it is believed that models do have a good skill reproducing basic physics. And so their outputs are just delivered to the public without this division, what is or what is not reliable from the point of view of what the problems that are solved are, you see? So that is why I think that there is urgency that this is done public, and this is subject to wide discussion. You see, I tell you that I myself was not
Anastasia,
aware.
it's clear. I would suggest to be synthetic.
I'm sorry, I feel so deeply about this.
We know that you feel so deeply about that, Anastasia. We are completely sure about that. And we have 86 people listening. We have 14 questions already asked on by mail, and 1, 2, 3, 4, 5, 6, 7 questions right now. So let's try to be reasonably quick in the question and answer. Thank you very much. Rob, would you please go?
Thank you. Thank you, Anastasia. Thank you, Ugo. Actually, I'd like to make a comment because basically we're having two problems which are obviously interconnected. One is climate destabilization, which has a lot to do with the disruption of the water cycle. And at the same time, we have the problem of global warming, which is interconnected, but is in fact a different phenomenon. Now, to solve global warming, or in fact find a new pathway to global cooling, basically we can look for a relatively simple solution, it seems, because once we add up the cooling effects of the biosphere of forests, which are basically a couple of categories, but let me just focus on evapotranspiration and increased cloud forming. Based on simple calculations, I think Anastassia already mentioned that there was a 2 watt per square meter difference. If you would add a certain amount of vegetation to the world, and with that increase the evapotranspiration and the cloud forming, you could correct the energy imbalance of the planet, which is only 1% between incoming and outgoing. So my proposal would be actually to sit down together with a lot of, I'm not a scientist, I'm a climate activist, but with the scientists in this group to see if we can have a model that's simplified, that simply looks for the solution. How much do we need to add in terms of forests in order to get an equilibrium in terms of global cooling? And that will also solve a lot of the problems that we have with climate destabilization. Thank you.
So also this, I think, deserves a quick answer from Anastassia, please. Anastassia, you hear me?
I know, Rob, your desire to present a convincing number and to start reforestation, but as you can see, I think that at the moment we cannot produce a number that will persuade a donor who is used to refer to global climate models while doing due diligence, you know. So at the moment, what I think should be done, that we need this discussion emphasizing that models are not bad. They are not bad. They are very useful. And this is our tool of learning. But at this particular moment, what they are telling us about vegetation is not reliable. And in this, if we have this discussion, then it is clear that the main thing is the precautionary principle. Start reforestation and preserve. So I think we do need this discussion and going from this end. Thank you.
Okay, thank you very much, Anastassia. Anna, do you have a comment?
Yeah, thank a lot, Ugo, and thank you a lot, Anastassia, as well, for brilliant presentation. I'm from Ecological Movement Biome from Kyrgyzstan, and I have no questions, but I have several ideas and thinking about this case. Based on Anastassia's presentation, it can be concluded that cooling from plant transpiration is association very deep with the operation of biotic pump. This means that we are all connected to each other much more than we previously thought. We live in Central Asia, for example, and for us, work of biotic pumps means water, without which life in our territory would be dramatically difficult or impossible. And there live almost 80 million people. That's why we have no chance for mistake. And I would like to focus in you on a very important principle. It's a precautionary principle in international environmental law. The lack of scientific data cannot be reason for not taking measure to conserve nature ecosystem, especially forest, hollow beyond complexes, and so on. Nowadays, already the theory of biotic regulation mathematically proves the work of the biotic pumps. This means that for us, extremely important, not just our local forests, but all forests in the continent, because they are to stabilize the climate and attract water in the middle of the continent, as Anastassia showed us in her presentation. And the second one, it's very important to understand how nature ecosystem organized. It's important for restoration ecosystem and for saving ecosystem. According to the researchers of Professor Shukurov, we know that the system forming element of nature ecosystem is the breeding population of predators. It's very important, and after my speech, I sent links for this structure. And finally, of course, we are ready to continue this discussion on the phenomenon of life on the planet and method of conservation and restoration of ecosystem. This is very important due to the context of global program for biodiversity conservation until 2030, and which was adopted in the framework of COP50. And I hope we meet many people, a lot of people here with whom we can continue this work for conservation of nature ecosystem. Thank you.
Thank you very much, Anna. This was a comment, very interesting comment. Thank you very much. I don't think we need to answer this, so we can go ahead. And Susan, please.
Hi, wonderful to be here. And I'd like to make a comment. I'm one of the co-authors on the paper on proforestation. So I'm a neuroscientist. My PhD is in biology. I collaborated with a climate scientist and an ecologist on that work. I want to let you know that it's under severe attack. It just means letting natural forests grow and evolve. It's nothing scary or like nothing unscientific. We went through all the data. But it's being branded as an irresponsible political movement, which, believe me, that's not my goal. So another piece of homework is maybe to look up the original paper and make sure that you understand what it means. It doesn't mean banning people. It doesn't mean banning responsible evidence-based management. My background is in biomedical research, so I'm always thinking of the first do no harm principle and the precautionary principle. And in terms of what's going on right now, we need to invoke that in the strongest possible terms and not, disturb something that could be working and functioning. And we all know there's a lot of conflicts of interest and habits and cognitive, commitments to ideas that make changing things difficult. But this is a concept that aligns with being scientifically responsible, financially responsible, aligns with public opinion, aligns with multiple scientific disciplines. And as a scientist and as a mom, if we can't do things that align with all of those principles, that really scares me. So thank you so much for bringing that up, Anastassia. I did not know that you would, and I want to thank you for bringing that up because it's a specific term that means a specific thing, and we need to get more specific about what we're doing.
Oh, thank you very much. Another extremely interesting comment.
Can Susan put her link, the link to her paper in chat?
Yes, it went through the comments, the chat, and when you can, Susan, please. Okay, it is already there. Okay, thank you very much. Now I'm pleased to have Anitra speaking. She's a fellow member of the Club of Rome, and she's an expert in ocean science. And so I think her comment will be extremely interesting to bring to us the other side of the planet, the watery side. Please, Anitra.
Thank you. I want to congratulate Anastassia for a very beautiful and clear with excellent illustrations talk that she's given us all. But I do want to bring up 3 small points. One of them, of course, is that the ocean forests which are very much under attack. They've had much more than 50% degradation, are immediately next to the sea, so that the transpiration immediately gets taken away by the circulatory mechanisms of the sea, as well as the air, which is very robust at the edge of the sea. And this is something which needs to be taken into account. The second thing, as a botanist, I wanted to say is that the tropical forests, it's been shown that the stomata, which is what drives forest transpiration, at the higher temperatures close, and at higher CO2 levels close, so that there's less transpiration of forests at a higher temperature, and it can be as much as 15% less. So that biological fact, I think, has to be taken into account. But particularly, I'm rather alarmed that you say that we should not only preserve, but not produce more forests, because of course Russia, USSR, has 20% of the world's forests, of which 85% have already been highly degraded or found absent. So Russia has 814 million hectares, and Canada has a lot, 315 million hectares. So not to increase those is quite a different thing than not increasing in many tropical places where there has been a great deal of almost complete destruction of their forests, say in Indonesia, or many of the Southeast Asian places, or many of the island. So I think this concept of freezing the forest, protecting that which we have, is a good thing in terms of the preservation, but is not a good thing. I do strongly believe we have to restore much of this 85% of our world's vegetation, which we have taken away for cities, for agricultural purposes, and so forth. And so that perhaps can be considered into the model.
Thank you very much, Anitra. Anastasia, perhaps you have a comment?
Thank you very much for your comment. I fully agree that we must restore. Fully agree. And but those forests that still preserve functionality, they are like hot spots for this restoration, from which ecosystem will further develop, and their value grows as we lose them. I'm not in the least against the restoration. These are all for it, but this is like the first thing that we should do. It takes centuries to restore forest. We shouldn't cut it now. Before, but I agree with you fully. Thank you.
Okay, thanks a lot. This is a truly very interesting seminar. Now, all the panelists have been pointing out that extremely interesting problems. Alpha, now your turn. You have to be just as interesting as the others, if you can.
Okay, cool. Well, I'm really happy to be here. I'm Alpha. I'm a physicist with the Climate Water Project newsletter. So I'm really happy to hear your model of figuring out the transpiration and how it cools, and really interested. So I just want to try and restate it, and you can tell me if this restatement is correct. And then I also have a second point too. So basically the amount of radiation coming in from the sun has to be re-radiated back out. And so normally without any greenhouse gases, the Earth would be at minus 18 degrees Celsius, and they re-radiate that radiation out. But if we imagine like a blanket around the Earth, so that's the greenhouse effect, then that blanket is further off the surface of the Earth, and so the outer edge of the blanket has to be at minus 18 degrees Celsius just to radiate the same amount. But if you have greenhouse gases, this blanket is higher up on the Earth, and so you have to heat it up a lot more, and so therefore you have to hold a lot more energy. So that's the greenhouse effect. But with transpiration, the temperature profile, as you're saying, is different, and so because the water, the latent heat, because it cools it at the Earth, but then when it turns into a cloud again, it releases that heat back, and so there's actually more heat a bit higher up, and so therefore that blanket doesn't have to be so high off the Earth, and so you don't have to heat up the Earth as much in order to re-radiate back out. So anyway, that's kind of reframing. I think sometimes people talk about global warming in that way. So just so I understand if that's the correct way of looking at it. And then my second question is, so the boreal forests are more usually northern than the tropical forest. So what difference does that make to like the height of the clouds?
I'm sorry, Alpha, we didn't hear you. Could you repeat your question, please? It didn't come out. We couldn't hear you well.
I don't know. You mean my first one or my second one?
Your last question. You asked the question. You said, "My question is," and then.
The first question. Yeah. Okay. The first question was just was my interpretation of Anastassia's transpiration model correct? And then second question is the boreal forests are more north than tropical and subtropical forests, and so do they create different heights in the clouds and because of the the latitude, and so does that make a difference to the whole model?
So I hope that Anastassia, did you catch the questions, because the audio was very disturbed?
Yes, thank you very much. Yes, you see, when we talk about the greenhouse effect, we usually think about, like you said, this upper radiating layer coming higher, radiating less, so the planet must warm, as you said. But when we deal with the redistribution of latent heat, the absorbers do change the amount, okay, in the first approximation. So the only thing that can change is the temperature profile, okay? So if you look at those graphs, you can see you cannot explain because the amount of absorbers doesn't change, so only the lapse rate, the temperature gradient can change. And so that is why it is the first order effect, the change of temperature gradient, you see? This is like another way to change the greenhouse effect. You can change the amount of absorbers, or you can change how energy travels between these absorbers, where it is released and where it is re-radiated. We change the flow of energy among these absorbers. And the second question, for sure, boreal forests and tropical forests are different because they have evolved to regulate different environments. And we need to study. We don't know how they do that, but we do know that forests control clouds, and that there are low clouds that cool and high clouds that warm. And so using this lever, any forest can regulate the climate for its benefit. So there is much to investigate here.
Okay, thank you very much, Anastassia. Now I would ask you to stop raising your hands. We still have 3 questions with hand raised, and we can go through these 3 questions, and then we will try to go through the 14 questions which have already been asked by email. So, William, please.
Hello, thank you. Can you all hear me?
Yes.
Anastassia, thank you very much. I'm wondering how whether you've studied or whether you have some sense of how forest canopy strata affect these phenomena thermally and hydrologically.
Could you repeat, please? Could you?
Yeah, I wonder how forest canopy strata, having photosynthesis at different elevations of the forest, or in forests that have a lack of biodiversity, the absence of forest canopy strata, how that dynamic will affect these principles thermally and hydrologically.
I cannot tell you about the transpiration of different strata, but one thing is very important is the roughness that is provided by forest canopy. Because this roughness by itself, that the presence of high trees is what modulates the vertical flows of energy and water vapor. So this is already very important. And if we talk about natural forests with well-developed gap dynamics, so the forest that is immortal, whose age distribution doesn't change, this should be particularly its roughness and its aerodynamic characteristics should be, I would expect them to find that they are optimal for all these processes. So like this.
Well, this is also a very interesting question, how the structure of the canopy affects this phenomena, but that, I would say it's a higher order question right now. We have to establish that there is a global effect of forest. And then, of course, actually, you have a very good point, William. This is an important thing to study. Thank you. And the next one, Peter.
Yes, thank you. Thank you very much, Anastassia. I very much appreciate your presentation. And also, Anita, for pointing out the role of the oceans. Do you have any comments on the role of grasslands and in transpiration too? I'm assuming that we're talking about forests, but maybe we can also talk about all vegetation.
Grasslands is a very, there's a great scientific challenge for ecologists, I think, because, of course, this idea that some grasslands are represent succession to some other more woody state. So when we speak grasslands, there shouldn't be all grasslands in every region. We should, go and see what is the actual ecosystem that can make most for this environment, that it is not degraded, it is not successional, it is not composed of alien species. So, of course, somewhere forests cannot grow due to physical limitations, and there will be grasslands or other vegetation which will do the job. But in many cases, forests just were destroyed, and where it is the case, I think that grasslands are probably less optimal. So we should study the natural to the degree that we can do that. Yeah.
So, Sue, would you please?
Yeah, hi. Anastassia, thank you for this really wonderful presentation and deep discussion of the physics and the problems. I'm thinking about the modeling as a problem, that we've got both terms that are inaccurate and weightings that are inaccurate. And you would like to influence the people who are the decision makers to use a more accurate model. Where are those decision makers? Is this UNIPCC? I ask this because science is this messy conversation, and it seems to me one of the things you're asking for is some very specific focus on decision makers to really reevaluate their use of models, which as a mathematical psychologist, I see as often being profoundly abused in our systems with failures to verify. I mean, right now we've got observations that massively contradict what the models predict, and people seem out of conflict about that. So where would you like to have an influence toward accuracy in modeling of the problem we're facing?
Thank you very much, Sue, for this comment. Indeed, we can ask, we are talking here and understand each other, but how this will translate to solutions.
Yeah.
And you can call me a conspiracy theorist, but on how global decision-making is done, they exist. So my personal view on the state of global climate models is that these big people were interested in CO2 business, and they were concerned how to get it right, because also it was used to push some agendas, which now we can see are pushed more efficiently by other means, like, unfortunately, wars. And this vegetation topic was not perceived by these big people as prominent. And so it was evolving like under the umbrella of this big CO2 business. And then, so without much, without much positive, so it evolved as it evolved. Then this idea about boreal forests warming the earth was around for 20 years. I think it percolated certain business interests who thought that while big agenda goes its way, we can use these interesting studies to push our own agenda. Because go ahead logging. You do a right thing saving the planet. And while the big guys were busy with the CO2 agenda, this topic was occupied by smaller but also big guys who are now advancing this coordinated effort. And you see, I mentioned that the article Science was renamed because it is about, boiling the frog slowly. And then it was decided that it was too fast, bad news for climate. So I really perceive it like a coordinated agenda. And my effort is to cry to those big guys, whoever are they, look, if you really are concerned about climate issues, do pay attention at what is going on with the vegetation studies. It is a complete disaster. What is being proposed is a disaster, totally unreliable. And my hope is that if we make this effort, somebody will listen. It will percolate. I don't know where they are, but they are somewhere. So when we talk to each other and reach out, they will take notice. Now, this most important topic is left to the next layer. You see, that's my how I see, and that's why I think that there is hope that we make this turmoil and it will change something.
It's like trying to overcome the deceptions of the tobacco industry, a similar process. Thank you.
I will now, if you like, because we still have 74 people connected, we go rapidly through the questions which were asked by email previously, and we see how we can answer these questions. Maybe not everything. We can leave Anastassia in peace for a moment. So let me go see. We have 14 questions here and more in the chat line and the question and answer. But let me go to those questions which were asked during the registration. So the first two were about the mechanism of how evapotranspiration can produce cooling, and I think that Anastassia explained that in her talk. The third question is interesting. Let's see. It says, I've been trying to convince an Australian colleague about the heat dissipation impact of evapotranspiration. he says that is not possible. It is constrained by the conservation of energy, and you can't fool the laws of thermodynamics. So I've seen this objection a few times. Your theory, Anastassia, is against the laws of thermodynamics. Now, maybe someone, not Anastassia, or you, Anastassia, as you like, can answer this question. Maybe Andrei Nefiodov, could you answer this question? Andrei didn't. Oh, anyone? Could someone raise your hand and think, I would like to try? Nobody knows about
No, I can. I think that we can answer this question. Actually, we did already answer that this is the heat does not return to the ground, as the colleague presumes, but it radiates while it goes to the area of descent. Okay, so what is important that the longer the warm air spends in the upper layer, the more heat will be released without interaction with the absorbers beneath. So it actually is related to the strength of the effect. But Andrei, I think, is going to answer another question about the Wien's law, right, Andrei? Yes. But yes. Okay.
Well, okay. Thank you, Anastassia. It's fine. Let me add an observation of mine to this point, and you could answer this question. If this objection, if you receive it, you can say, well, think of an air conditioner. An air conditioner is a machine that creates heat because that's necessary by the second law of thermodynamics. Nevertheless, it can cool your room because it transfers heat from your room to outside, and air conditioners cannot beat against thermodynamics because they exist and you can buy them at your hardware store. So this is, I think, how to answer this question. And Andrei, would you like to intervene now?
I would like there was a question concerning water vapor window, and I would like to give a comment on it.
Okay, so, that's exactly the question I wanted to raise now. It's question number 7. So please, Andrei.
Yeah, that was a question. According to the Wien's displacement law, the black body radiation curve for different temperatures will peak at different wavelengths that are inversely proportional to the temperature. Due to the lower tropospheric temperature, radiation from latent heat released upon condensation falls into the atmospheric spectral window, the wavelength interval where greenhouse gases do not absorb thermal radiation and therefore escapes to space. Thus, transpirational cooling results from this effect. and the picture is the following. So this spectra shows the radiation which we receive from the sun, and this part corresponds to the thermal radiation which is going to space from the east. And we see that this area of wavelengths exactly corresponds to the water vapor window greenhouse gas, which allows to emit this radiation into the space. There are some lines and pieces of spectra which act as absorber, but exactly in this area where we have thermal radiation from the east, there is a window, open diapason of wavelengths, which allows thermal radiation to leave the planet. So this is a question, but please go to the next page. First of all, to answer the question, let's come a little bit back and consider what is a black body. Black body is an idealized body that absorbs all the incident electromagnetic radiation, regardless of wavelengths or angle of incidence. A black body in thermal radiation that is at a constant temperature emits electromagnetic black body radiation, but in another wavelength domain. Let's have a look as an example. In the sunny day, all the sunlight goes to the room in the house. And if you are inside of the room, you see that it's full of light. But outside, if you look at the window, you see that it's dark, because the sunlight is splitted. Photons of sunlight is high energetic. It's split on about 20 photons of thermal radiation, and the light which is emitted from the room is not in the visible diapason. It's shifted to the thermal radiation, and it occurs because sunlight interacts with the matter. And this is what we have. This is exactly an example of black body. So it absorbs all the radiation and shift it to the thermal radiation diapason and emits again as a body, as a black body, but in another energy scale. Next page, please. And the spectral distribution of this radiation is described by what is called Planck law. It was discovered in more than 100 years ago, and it was actually made within the framework quantum theory. And this is a formula which describes this, this behavior. I have a few graphs. We can please shift it a bit. If you try to present this formula on the graph, for particular temperature, it's dependence of intensity of radiation with respect to the wavelengths. And the meaning of this graph is the following. The black body emits radiation different depending on the wavelengths. If you fix the temperature, there is a, for example, 500, what is the 5050 Kelvin, this green curve. You see that near this area, there is a biggest amount of emitters, and we have biggest amount of intensity. But if you have another, take another point of wavelengths, then it becomes lower. So at this particular temperature, 500 Kelvin, we have less amount of emitters with respect to this one. And it's, there is also what is called Wien's displacement law. It was discovered before the Planck's formula was written, and it can be obtained from the general Planck's formula. Then shows that the wavelengths which corresponds to the maximum of intensity of emission, it's reversely proportional to the temperature. So if you decrease the temperature, then the maximum of the intensity is shifted. It's shifted to the according to if you decrease the temperature, then the wavelength becomes larger. That's the message which is followed from the Wien's law. And the here just a comment. We have on the left graph emission from the sun, and the theoretical curve which is fitted to this spectrum. And when we fit this curves, we can identify the temperature which corresponds to the sun. It's almost 6,000, just less than 6,000 Kelvin. And go to the next page, please. So when you have a window and reduce the temperature, then it doesn't matter, it's not so important where the maximum is located. The important characteristic is the integral of this intensity for all the wavelengths. And if you integrate Planck's formula for all the wavelengths, you receive what is called Stefan-Boltzmann law. And the black body emittance, the power of radiation per unit surface, is proportional to the temperature to the 4th degree. And it means that if you decrease the temperature, then you decrease the power of emissions of the radiation. So if you decrease the temperature, then the emittance is also reduced. So one can play around with a little bit with limits of integration, but this dependence more or less robust. So it doesn't matter whether you can shift the maximum curve, but integral actually is proportional to this temperature to the 4th degree. So as you have seen, this window has nothing to do with the transpirational cooling, but almost all the thermal radiation goes through it. So, and this dependence is because the intensity with decreasing temperature becomes lower. Even the maximum can be within the window, it doesn't matter. So reduces the temperature, we reduce the integral quantity, power of emittance, power of radiation. I finished, thank you.
Okay. So essentially, Andrei, if I understand correctly, you said that this shift is not a very important factor in this.
Yes.
Okay.
Yes, right.
Which
shift
I think
it's not the integral.
It's not the important thing. It is the fact that evapotranspiration warms some higher layers in the atmosphere, and these higher layers emit in other layers, which eventually will warm them and to increase the emissions towards outer space. But it's you know you see how many things. It's very interesting. Now,
can I answer one important question that was now asked in the questions?
Mm-hmm.
It says, what are the wavelengths of radiation from condensation, and do they match any atmospheric window? This is what Andrei was now telling. First of all, I just summarize what Andrei said. Please understand that there is the window, okay? And there are two Planck distributions for higher temperature and for lower temperature. And if you calculate how much what share of radiation falls into this window, so for the higher temperature, for the lower temperature, it is lower share. Like on the surfaces, it is 19%. And on top, it is 18%. Because despite the fact that, Rob, you are right, that the maximum moves more into the window, but the distribution becomes flatter at the same time. So much more goes everywhere. So we should stop talking about this. This is incorrect and has nothing to do with the global transpirational cooling. This is one thing. Another thing is that what is the wavelength emitted from condensation? Please, we need to understand what happens when condensation occurs. There is no emission of radiation. If there was emission of radiation upon condensation, then hurricanes, when there is a very strong upwelling and huge rains, they would be radiating as superstars. You know, they had such intensity. This is not what happens, but it is a good question. How does evaporation and condensation produce cooling or warming? For example, if we have a saucer in the room with water, how does it make it cool? How? How? What happens? And I can tell you a way how to visualize it. Because molecules in the liquid stick together like we stick to the earth with the attraction forces. And so, but they are not all equal, these molecules. Some are more energetic and others are less energetic. And only the most energetic molecules can break away from the liquid to the vapor phase. And imagine that there is a crowd demonstrating against something like COVID restrictions. And there is the police, which takes the most active demonstrants again from the crowd. And the crowd calms down. And this is exactly what evaporation is doing. It removes the most energetic molecules from the liquid, so the liquid cools. But those molecules that arrive to the vapor phase don't make it warmer because they lose their extra energy when they work against the attraction forces. So this, and so evaporate, and the reverse process happens during condensation when the less energetic molecules collide and have no energy to break apart, and so they form this droplet. And the remaining gas, because of that, becomes relatively warmer because the least energetic have left to the droplets. And so there is no like release of something, but just this very tricky, you know, selecting of molecules. And so this, and then this kinetic energy, extra kinetic energy of molecules that formed, then after a lengthy process of excitation of the greenhouse gas greenhouse absorbers, it is radiated to space like any other radiation captured by them from the earth, from whatever. You see? So condensation first produces just warming, just making it relatively warm. You see? And then this energy slowly like finds its roots through radiation to space. And that is why the longer the air, this warm air stays in the upper atmosphere, the more heat will be released more directly to space. Okay, thank you. This is an important question to understand. No radiation immediately upon condensation.
Great explanation, Anastassia. We understand. It's we see that you feel a lot for this, indeed. And Rob, do you have a comment?
Yeah, this is Marcel de Berg on Rob's account.
Okay, sorry.
I'd like to give more detailed information about the phase change and how water vapor can emit infrared radiation. When water vapor goes to a lower energy state, when during a phase change, bonds are formed, hydrogen bonds are formed. When hydrogen bonds are formed, infrared radiation is being released. Anastassia, you were talking about why in a hurricane you don't get lots of radiation. That's because water in a liquid form can absorb all the infrared radiation of the spectrum. The difference is that in the gas state, it can't. So what happens that's the research done by Tartachenko and Perelman in the 70s, two Soviet scientists. What happens in the first stage of when water vapor goes back to water, an electron goes to a lower energy state. When that happens, electromagnetic radiation, infrared radiation is being emitted. It's in the gas phase, a gas is not a black body. It's a discrete spectrum. So water and matter can act as a black body, but gas cannot act as a black body. So when the water vapor goes back, it emits infrared radiation. When it's in a hurricane, there's a lot of water already around that water molecule, and all that water in the liquid form absorbs all the energy. But when it's in a cloud, the phase change occurs at the top of the level of the cloud. So first you get a transformation, and that's called Tartachenko and Perelman phase 2A. Then you get first the infrared radiation. And that infrared radiation, according to Perelman and Tartachenko, lies within the atmospheric window. Of course, you also have water droplets at that moment, but those water droplets are below the phase change level. So 50% of the radiation goes down, 50% of the radiation goes up. The infrared radiation lies within the atmospheric window. So the radiation that's going upwards to space lies within the atmospheric window. So all the greenhouse gases, water vapor, and carbon dioxide are transparent for that radiation. So the radiation going up.
Rob, excuse me, it's very nice, but I think we are going into details which are.
Yeah, but this is the essence. This is the discussion.
Yeah, but
Anastasia is talking about kinetic energy.
And this factor is important, but the important thing I think is the transfer of heat. Then of course the wavelength will change a little because the temperature changes. Then there is a Wien's law, which necessarily
this has been a discussion. This has been a discussion in the email.
Yeah, okay.
If it's only kinetic energy, yeah, and what Anastasia was talking, if a gas molecule goes to the liquid phase, yeah, then the gas molecule with the lowest kinetic energy goes into the water vapor. Then Anastasia is saying that the kinetic energy, the F's kinetic energy goes down. That's correct. But the total energy is also going down.
Rob, I think you should discuss that with Anastassia. This goes a little bit beyond what most of us can understand.
But this is the crucial part of the discussion in the email. That was the reason
yes, I saw the discussion, but you see, doesn't change so much the main point. We have this effect, which, according to what Andrei told us, is not so much related to Wien's law, but I mean, when you have an air conditioner, you transfer heat from some place to some other place, and that is affected. But it's not against the laws of thermodynamics; it cannot be. But I think
this is the crucial part of the story.
I agree with Marcel that this is an important point, and I can respond to you. Condensation, when you look at it, like what exactly the process, what exactly goes on there, I agree with you that it is a very complicated process with lots of things that we may not even know now. And of course, there can be photons emitted and everything, but the problem is that there is, an equilibrium between different, degrees of freedom. So even if there are photons emitted, as you say, they are immediately thermalized with other degrees of freedom, kinetic energy. So it basically doesn't. So this is transient effect, which has nothing to do with radiative transfer, because condensation, as you describe it as a non-equilibrium process. Strongly non-equilibrium. And when we take this view, yes, there are lots of processes that occur there. But in the atmosphere, these complicated processes don't matter, because when acting as a black body, as you say, there is all energy follows Boltzmann distribution. So you cannot have these photon emissions. It would be like a laser. You see, this amount of thermal radiation. It doesn't happen. It is immediately transmitted to kinetic energy.
It's on quantum.
So what you're saying is correct.
Ladies and gentlemen, please, it's very fine, but this kind of discussion cannot be done in this format. I would ask you, I think we still have time for a couple of comments. What about, would you like to raise your hands, whoever likes to have comments?
If we have Jan Pokorny in the audience, he was planning to answer one of the questions.
Okay, Jan, would you?
Good evening from Central Europe. Can you hear me, please?
Yes, thank you.
Yes, okay, so it was a question about the proportion between photosynthesis and evapotranspiration. I will not use any pictures. I think it's a basic knowledge. Plant takes one carbon dioxide molecule, release one oxygen molecule, and evaporates several hundred molecules of water. So, and this is a process which is coupled. And then was a question, what is the relationship between biomass, which is produced during 1 year, and the evapotranspiration? In our conditions, in temperate zone, 1 kilogram of dry mass is produced by photosynthesis per square meter per 1 year. And we have then 400 grams of carbon there and energy about 5 kilowatt hours. However, during this season, about 600 kilograms of water was evaporated in order to make this 1 kilogram of biomass, and 500 kilograms of water represents about 350 kilowatt hours energy, which was, we can say, dissipated, or which was used for equalization of temperature differences. It's all. I will not disturb more, because just when we see the low temperature in forest, low temperature in grassland, it means that it works in comparison with the dry, even lighter sand and so on. Thank you.
All right, thank you very much. That also was a clarification on the point that was asked. Zuzka, how long, what do you think? How long should we keep going?
We have 3 raised hands among the listeners. Probably we can hear them like rounding up. We have 3 raised hands, but not among the panelists, but among the listeners.
Yes.
Marina, can we enable them to speak?
Just before they answer, I would like to say that Dr. Anastassia Makarieva would like to continue this conversation. So we will hope to organize more webinars for those whose questions were not asked. And we hope we will get better at it. And we will need all of your help to get this, to make this message simple. Thank you.
All right, so what do we do now? What do you think?
Marina, you could ask the questions.
Yes. Do we have more questions from the Marina? Marina, would you like to intervene? Could you please, Zuzka, activate the microphone from Marina Frontasieva?
No, it's a mistake. I'm greeting all of you. Just, I listen attentively, but I'm not enough knowledgeable in this respect. But thank you very much for giving me possibility to listen to your talk and to exchange your opinions. I'm very much excited. Maybe later I'll be more knowledgeable. Thank you.
Okay, thank you very much, Marina. It's a pleasure to hear from you. And Max, would you like to intervene?
Only to say thank you very much from New Zealand. I'm a New Zealand farmer that's been following this debate for many years, and I'm very, very grateful for all your work.
Thank you, always. Thanks, Shane, Emmanuel. Shane, you raised your hand.
Hello?
Yes, we hear you.
Yes. Okay. It's my question, it's a little bit, so my background is a botanist and a biochemist, but maybe I'm having trouble understanding the physics of let's say, you know, an area of there's the same amount of solar radiation hitting the earth, you know, let's say at one spot, depending on what the ecosystem is. So if how are plants like let's say a forest, how are they more effective at this evaporation than an open water body? Because it's all driven by solar radiation. Is it that it's the solar energy that powers the transpiration, so it's more energy absorbed, but that's being converted to vaporizing the water, compared to say an ocean? Is an ocean reflecting more? Or could somebody please try to explain that?
It is a good question, Shane. And,
may I interfere? Yeah.
Yes, please. Jan,
thank you. So I am plant physiologist. Welcome, botanist. So first, it's a just physical surface, water, and plants, they have a so-called, we speak about leaf area index. So in forest, you have 10 square meters of leaves above 1 square meter of ground, and each square millimeter of leaf has 100, 200 stomata. So it's a living organism which really gets a lot of energy and which controls evaporation. And with the life, we will control climate. I could now speak 1 semester.
Thank you very much. Yeah, very good answer. Very good answer.
Sorry, the difference though, where is the energy, the extra energy? Because it's the same energy that comes in. So what happens to the energy from the water, for example? I understand the more surface area, but it's still the same energy in. So
first,
maybe I'm
water,
not getting it, yeah.
Yes, water reflects only about 10%. Then water evaporates, but not more than if we have large water, not more than the plants which have enough water. Plants reflects about 20%, and then depends how much water they have. And normally, if we have about 50, okay, you have 1,000 watts coming, 200 watts will be reflection, about 100 watts would be heating, about next 100 watts would be flux to the atmosphere, and about 50% would be evapotranspiration. And concerning large water, it will take more energy and heat itself, and the evaporation will be a bit lower than the vegetation which has enough water supply. However, if you have vegetation or small water body, then you have increase of hot air, which will increase the evaporation of water because it cannot close the stomata, whereas the grass or wetland, even reed, will close stomata if it feels that something happened and that it would die. I know that I answered a bit complicated, but we are dealing with a living system.
Thank you, Jan. I think I begin to understand.
Yeah. It's you heard it.
I am happy to
no, but you, Shane, you have a very good question because the energy in is the same, doesn't change. So what happens? And Ian explained it. You depends how it is distributed. It could just warm the surface it hits, or it can be used for evapotranspiration, and that's exactly what happens. And thank you for this question. So we have first a question by Mikhail or Mikhail.
Okay, and I want to respond to this when that's done.
Mikhail, please.
Hello, everybody. I have very short comment about that, especially about photosynthesis process, because we know that it's all vegetation is results from photosynthesis, and we have sky we have sun on the sky, carbon in the atmosphere, and water on the ground. And problem is about management of rainwater on the landscape. And if water we are pushed to sea, after that it is increase of carbon dioxide in atmosphere and overheat whole system. On the physical approach, it is, I think it is more important is transforming of solar energy to latent heat or to sensible heat. If we have no water in ecosystem, after that it's solar energy transformed to sensible heat and overheat and create this heat islands. And problem is because we loss of water from the system, and if we harvest water on the ecosystem, after that we are support producing of photosynthesis, growing of vegetation, and transform of solar energy to latent heat. And latent heat flow by vapor water to atmosphere to cooler zones, and after condensation and creation of rain, starting to transform of latent heat to sensible heat. And it is necessary to deeply make research about this transforming of energy, not only about the radiation. It is my recommendation for this discussion. Thank you.
Thank you very much. Yes, good point. Sue?
I just had a quick thought about evaporation from trees, which is that comparing to, say, the surface of the ocean, you have a square meter, but the trees are actually pulling water from their root system and a massive soil biome that also brings water to their root system and the leaves, so that the area or the volume from which the water is coming is actually much greater than the surface just looking down on the plant. And I don't know if anybody's sending any work on that, but the fueling of that evaporative cycle by the soil biome, the mycorrhizal network, and the root system seems to me an important factor in the difference in evaporative power.
So eventually everything is linked. The oceans, the microbiota, the soil, the trees, the leaves, the atmospheric rivers, and all this movement. It's fascinating. It is fantastic. We have to thank Anastassia and the others who worked on this in this field, because it is really, really, really fascinating. I'm amazed that we could understand a little of this complex and incredibly complicated system, which also is mostly responsible for what we call planetary homeostasis, which is one of the main contributions to science of Anastassia and Viktor Gorshkov, who developed a number of these concepts. Okay, sorry. Any more questions? Yes, there is a question from just somebody asked me how. I'm still interested in question number 11, and we can go through this one quickly. How contiguous does forested land need to be for the biotic pump to operate? Anastassia, can you answer this?
Oh, okay. First of all, if we recall that at a certain point, life was all in the ocean, and then at a certain point it began to colonize land. So apparently it found a way to start from like a very small, not contiguous region. And so the answer is it depends where you want to get the biotic pump functioning. If you want to get it functioning in the middle of the Australian desert, then you will have to have a contiguous forest from the ocean. But if you start from the ocean, then you can gradually improve your conditions with small increments, starting from like what we call a wet spot. therefore, any restoration, eco-restoration effort should start with a very careful climatological analysis of what is this area, what it can offer in terms of moisture transport and conditions, and that's it. And I was asked about some resources. I would want to draw your attention to two very important and interesting publications of Dr. Antonio Donato Nobri, who is the scientific leader of the biotic pump greening group. So you can see he wrote this famous, widely known Future Climate of Amazonia report, and he also, like Ugo, is like a champion of this holobiontic view of things. And to the Shane's also answer, how I answer it, the energy is the same whether we put like it into the oven and burn it, or if we feed a scientist and he produces a paper with the, you know, a discovery. So this is the energy doesn't matter as much as the genetic program of the forest compared to the simple water body that allows the forest to transpire as much as is needed when it is needed and to get most of the atmospheric conditions. Like imagine, like look at the flying insect. We cannot we cannot predict its flight not knowing its genetic program just from the aerodynamics alone. So it is all about inherent complexity of what processes are initiated by the forest. For example, when it is too dry, the water body will continue to evaporate and even more. But the forest can shut down evapotranspiration because it knows that if he transpires but no condensation occurs, it will lose its water. So it is all about information that is that governs this the biotic pump function. And this is here it is also very important that plants function on the basis of solar radiation, which has this 6,000 Kelvin temperature, and not on the basis of thermodynamics of the Earth, which is the temperature 300, low ordered compared to the sun. That is why forests can do things that others don't.
And that's why, that's how.
And Uga, and you could continue this, the other question about the Prigozhin's like.
Okay, well, look, it has been 2 hours and 15 minutes here. Oh gosh, I'd say let's do this, ladies and gentlemen. We have one more raised hand by Jim, and we listen to Jim. Then we very briefly we tackle the question about Prigozhin. But Jim, would you like to intervene, please? Jim, do you hear us?
Jim Laurie, if you can unmute and turn on your camera, maybe.
I can unmute. Okay, I've been watching this, and but I haven't been in the inner circle, so to speak. I think the thing that my model is much simpler in some ways. The ocean is warming, and 93% of the energy that is held on the Earth is going into the ocean. And what I see is that bare ground heats much more than vegetated ground. And so what happens, if it rains on bare ground, it runs into the rivers or whatever, we have flash flooding and so forth. That water carries all that heat to the ocean. And it's kind of like every time we have a high tide, you know when you go out onto the beach, you know, if you're on the sand that's dry, you tend to walk towards the sand that's wet because your feet don't burn. And every time that the
water rises on the tides, it takes energy back to the ocean. And what I think the number is the amount of accumulated energy in the oceans. Now, what Anastassia is doing for us is she's showing that if we have vegetation everywhere, that's great, but it's not just forests, because as you move inland in the continents, we realize the importance of how grasslands and grazing animals co-evolve. And much of what we call deserts now used to be grasslands. And I think Judy Schwartz has worked on this a lot, and I think we could learn a lot from hearing more from her. But just the idea that we've got to eliminate bare ground. In some places that's forests, you know, and in some places it's grasslands with animals being an adjunct to that. So, you know, that's something you can monitor very easily by sending the drones over or the satellites over or whatever. We can see the bare ground, and it's much more than it was when I was born in the 1950s. So we've got to eliminate bare ground. We've got to make bare ground illegal, you know, and that's just, so that's my short thought about that. So thank you.
Good point. We understand it is, I think it is exactly what we are trying to say here. We need forests, not bare ground. And this first point that Anastassia was making at the beginning, that some people seem to propose that we should cut the boreal forests to cool the earth. And I think personally that it would not be a good idea. I would now go to the question number 15 about Ilya Prigozhin. And do we have somebody prepared to answer to this question?
May I just take a very short commercial break? It is 2 hours after the webinar. I would just suggest we want to thank you to all who have to go. We will say thank you to them. And after this, we will continue the conversation. Is that okay, Ugo?
Yes. You mean that, I'm not sure. What is your proposal? Could you?
I don't know. Can you see the screen? I just want to say
New Year, and thank you very much. And yeah, that I can see that.
Yes.
But we can keep going forever in principle. But at some point, I think we will lose most of the panelists. Prigozhin, anyone would like to answer the question number 15? If not, I can try that. Okay, just to, so Prigozhin is a great scientist. He's the one who developed this fundamental concept, which is dissipative structure, which includes all living creatures, but also all complex systems like hurricanes, ocean currents, and everything which feeds on an energy potential, and then it dissipates it as heat. That's the way we humans work. We are machines which take in energy, actually metabolic energy, food energy, and we dissipate it into the environment as heat. And we may be more or less efficient in doing that. Exploiting the difference in potential energy, we can be more or less complex. And we tend to organize as good dissipative structures, which is what we are. Everybody here, even Anastassia, is a dissipative structure. Anastassia, you have dissipated a lot this evening, indeed. And we do that, but it is not everything. No, not in all conditions you can have dissipative structure. You go to Mars, where probably there is no life. There is sunlight on Mars, not as much as on Earth, but we don't have the right conditions to create those dissipative structures which are typical of Earth. So it is a dynamic phenomenon which started long ago, and these dissipative structures tended to evolve and to create more and more complicated structure, which humans are doing a lot of damage to the ecosystem because they are very complicated dissipative structure. The question is very interesting here. What is going to happen in the future? Can we maintain the present complexity of the ecosystem, which is where the ultimate answer is no, because you probably know that the sun is increasing its luminosity over time, so over millions and hundreds of millions and billions of years. So we know that eventually the Earth will be sterilized by the solar radiation in about maybe 500 million years, maybe 1 billion years. So then there will be no more dissipative structure. But then it's an interesting point that humans could do something to hasten this process and sterilize the planet much earlier than the natural evolution of the star, which we call sun, will do. So the question is, if we deforest the Earth, deforesting, remove the trees, and we have different dissipative structure. We have typically what we call savannas. And savannas may be an adaptive system to different conditions in the ecosystem related to an increase, a gradual increase in solar radiation, which has been happening during the past 500 million years or so. So the system might naturally lose the forest, because the forests were by Sue, it was a pleasure. The forests were created in a condition in conditions about 350 million years ago, in conditions which are not the same as today. So the future may be savannas, which is a dissipative system, just like forests, but probably less efficient in terms of the processed amount of energy and also water. This is an interesting point, but savannas probably do not have the same efficiency in creating evapotranspiration that forests have. So from our viewpoint of humans, we should try to keep the system as it is, because we developed probably as arboreal creatures back a few million years ago, and we still have a certain relation with trees, and savannas are not the same thing as forest. They are not the same thing. And so the question is very interesting. I think we should keep forests and limit savannas, because it is not the same kind of system. And there is an interesting point here on how animals act sometimes to destroy forests and create savannas, but this is a very complicated question that Anastassia and Viktor Gorshov have examined in some of their papers. And that's another good point, which I think highlights the extreme complexity and fascination of these systems. And this is what I personally can say about Prigozhin. And maybe, John, do you have a last comment, and then we close?
Sure. First, I want to thank and congratulate Anastassia and the moderators on doing a really fantastic job. This is all much, much clearer and more understandable than it was before. I have a question that I'm happy to have be considered after we close. But it seems to me that one of the key insights is that the amount of infrared radiation is going to vary as a function of the amount of evapotranspiration. And that might be measurable over open ocean and over boreal forest and in a few other key places. And I think Anastassia's theory suggests that those should be substantial and measurable effects from satellites. I'm wondering whether there are some data that could be obtained that could demonstrate that we're not violating the laws of thermodynamics here. We're actually latching on to a really important principle that can be shown to be significant.
Anastassia, I think these data exist, right?
Do you mean the radiation, like measuring the radiation where?
Yes,
where?
Measuring radiation out into space, where over areas of a great evapotranspiration and comparing it to areas of low evapotranspiration. I do understand that air currents circulate, but it's a big planet. Maybe there are places where we could get some strong signals.
First of all, it is very important to study this. But you see, as we have seen, evapotranspiration and condensation is not equivalent to the release of radiation. So it takes time, and travel of air in the atmosphere to radiate it. So that is why we are talking about global cooling, which is not easily measurable. But locally, of course, we can see it, and it is well measured. For example, there is a very good recent study showing that undisturbed forests in the Amazon buffers partially the greening, and it warms much less than the disturbed forest. This was studied by Sprocklin and colleagues. So it is well measured, the local effects. But to trace it globally, it would be difficult. What I think should be done, is to study how the cloud cover differs over disturbed and non-disturbed forests, because really cloud cover is the lever with which the forest could control the climate. And so if we are to seek this mechanism to see it, should be there, I think, in the first place. Yes. And there is already a study showing that a cloud cover deteriorates and becomes more destabilizing after clear cuts in Siberia, for example. But it is very recent research.
Ladies and gentlemen, I think we could consider in thinking of maybe closing. What do you think? Poor Anastassia has been destroyed by this effort, this incredible effort. And thank you very much, Anastassia. It's been fantastic. And please clap your hands for real, or maybe clap using the clapping hands. There is a reaction that goes clapping hands, so you go with that. And I would like to thank Zuzka for organizing, and Anna, and all the others. And I think we should do it again. And it's enough. And thank you, everybody. And see you, I hope, next time.